Right now, trillions of miles from Earth, an invisible battle is unfolding across the darkest stretches of space. It is not a clash of stars or a collision of galaxies, but a gentle yet unstoppable dance between speeding cosmic winds and the sparse gas and dust that fills the void between star systems. This dance creates one of the most beautiful and misunderstood phenomena in astrophysics, the bow shock, a glowing curved ripple that cuts through the interstellar medium like the prow of a ship slicing through a calm ocean. If you've ever watched a speedboat race across a lake, you've seen the basic shape of a bow shock, an arc of water rising ahead of the hull, pushed aside faster than the water can naturally flow. In space, this same logic applies, but scaled to sizes that defy human imagination. Bow shocks aren't just pretty cosmic structures, they are boundary markers, particle accelerators, and time capsules that reveal how objects move, interact, and shape the universe around them. Today, we're diving deep into the science of bow shocks, from the small protective arcs surrounding Earth to the colossal waves wrapping around runaway stars and colliding galaxy clusters. We'll explore how NASA's most daring missions rewrote our understanding of our own solar system's bow shock, and why these ripples hold the key to unlocking the secrets of the interstellar medium, the invisible stuff that makes up 99% of the visible universe's volume. Let's start close to home with the bow shock that protects every living thing on Earth. Our planet isn't just a rock orbiting the sun. It has a giant magnet surrounded by an invisible magnetic bubble called the magnetosphere. The sun constantly blasts out a supersonic stream of charged particles, known as the solar wind, racing outward at millions of miles per hour. When this solar wind hits Earth's magnetosphere, it can't just pass through it, slams into a barrier. Because the solar wind is moving faster than the speed of sound in space, the particles can't warn each other of the incoming obstacle. They pile up, compress, heat up, and slow down abruptly from supersonic to subsonic speeds. This sudden shift creates a thin curved boundary, about 56,000 miles above Earth's surface, our planet, bow shock. This isn't just a random space feature. It has Earth's first line of defense. It deflects most of the sun's harmful charged particles, preventing them from stripping away our atmosphere and irradiating the surface. Without this tiny bow shock, life, as we know it, could never exist. Every magnetized planet in our solar system, Jupiter, Saturn, Uranus, Neptune, has its own bow shock, each shaped by the strength of its magnetic field and the speed of the solar wind at its distance from the sunday. Even comets, with their fragile tails, form bow shocks as they speed through the solar system, their dusty atmospheres colliding with the solar wind to create glowing arcs that stretch millions of miles across space. But the most famous bow shock story in our solar system centers on the sun itself. For more than 50 years, astronomers had a simple, elegant model. The sun creates a giant magnetic bubble, called the Heliosphere, which wraps around all the planets and extends far beyond Pluto. As the sun orbits the center of the Milky Way, it plows through the local interstellar medium, a thin fog of hydrogen, helium, and dust. Scientists predicted that this motion would create a massive bow shock ahead of the Heliosphere, at about 230 astronomical units from the sun, more than twice the distance of Pluto. This bow shock was supposed to be the ultimate boundary mark, where the interstellar medium slowed from supersonic to subsonic speeds before hitting the heliosphere's edge, the heliopause. Between the termination shock, where the solar wind slows to subsonic, and the heliopause lies the heliosheath, a turbulent transition zone. For decades, this model was taught in every astronomy textbook, and NASA's twin Voyager spacecraft were sent out in 1977, partly to find this legendary bow shock. Voyager 1 and Voyager 2 are humanity's greatest interstellar explorers. They left Earth long before smartphones, before the internet was widespread, and they've been traveling outward for nearly 50 years. Voyager 1 crossed the termination shock in 2004 at 94 AU and became the first human-made object to enter interstellar space in 2012 when it passed the heliopause. Voyager 2 followed, crossing the termination shock in 2007 and the heliopause in 2018. Both spacecraft sent back data that shocked the world. There was no bow shock. Not a faint one, not a weakened one, none at all. Then came NASA's Interstellar Boundary Explorer, or IBEX, a small satellite launched to map the edge of the heliosphere. IBEX confirmed the Voyager findings in 2012, publishing a paper in Science that upended half a century of theory. The reason: the local interstellar magnetic field is stronger than we thought, and the sun's speed, relative to the surrounding cloud, is slower than calculated, about 52,000 miles per hour. Together, these factors prevent the interstellar medium from slowing enough to form a classic bow shock. Instead of a sharp shock wave, our heliosphere creates a gentler bow wave, a gradual compression of gas, without the sudden density and temperature jump that defines a true bow shock. This discovery isn't a failure. It is a triumph of exploration. It taught us that space is far more complex and dynamic than our models predicted, and that we can never stop questioning the assumptions we hold about the cosmos. While our own solar system lacks a bow shock, the rest of the universe is filled with them, some so large and bright they can be seen across millions of light years. The most stunning bow shocks form around runaway stars, massive young stars that are ejected from their birth clusters at extreme speeds, often by gravitational interactions or supernova explosions. These stars race through the interstellar medium at tens of thousands of miles per hour, faster than nearly all other stars in the Milky Way. Their powerful stellar winds, far stronger than the sun's solar wind, slam into the surrounding gas and dust, creating brilliant arc-shaped bow shocks that glow in infrared and visible light. Take Zeta Ophiuchi, a blue supergiant, 20 times more massive than the sun, 80,000 times brighter, and speeding through space at 54,000 miles per hour. The Spitzer Space Telescope captured its bow shock in stunning detail, a curved, glowing ribbon of dust and gas stretched out for trillions of miles, like a cosmic comet's tail. Another example is Kappa Cassiopeiae, another runaway supergiant, whose bow shock emits gamma rays as it accelerates electrons to nearly the speed of light. These stellar bow shocks aren't just visual spectacles. They are cosmic particle accelerators, some of the few places in the universe that can boost particles to the ultra-high energies we detect as cosmic rays. They also compress interstellar gas, triggering the formation of new stars in their wake, creating a cycle of life that sustains galaxy growth across billions of years. On the largest scales, bow shocks form around colliding galaxy clusters, the most massive structures in the universe, held together by gravity. These clusters are filled with hot ionized plasma, and when two clusters crash into each other at millions of miles per hour, the smaller, denser cluster plows through the larger one's plasma, creating a bow shock that stretches for millions of light years. One of the most famous examples is the Bullet Cluster 1E 065756, observed by NASA's Chandra X-ray Observatory. The X-ray image shows a clear, curved bow shock ahead of the bullet-shaped smaller cluster, a wave of superheated plasma that is millions of degrees hot. Studying these cluster bow shocks lets scientists measure the speed of the collision map, the distribution of dark matter, and test the laws of plasma physics under the most extreme conditions in the universe. These shocks are so powerful they shape the evolution of entire galaxy clusters, heating gas and preventing it from cooling to form new stars, altering the fate of thousands of galaxies at once. What makes bow shocks so special is that they connect every scale of the cosmos, from the tiny shield around Earth to the colossal waves that shape galaxy clusters. They are universal structures governed by the same basic physics, whether they form around a planet, a star, or a cluster of galaxies. They teach us about how supersonic flows interact with obstacles, how magnetic fields shape cosmic structures, and how energy is transferred across the universe. The interstellar medium, once thought of as empty space, is actually a dynamic, active environment, and bow shocks are the visible signs of its constant motion. Every time we observe a bow shock, we re-seeing a snapshot of cosmic motion, a record of how an object moves through its neighborhood, how it interacts with the stuff around it, and how it leaves its mark on the universe. The study of bow shocks is far from over. New telescopes, like the James Webb Space Telescope, are capturing sharper images of stellar bow shocks than ever before, revealing fine filaments of dust and gas that were previously invisible. Future missions will explore the outer heliosphere in more detail, hoping to understand the gentle bow wave that surrounds our solar system. Every new observation brings new surprises, reminding us that the universe is full of hidden structures waiting to be discovered. Bow shocks are more than just ripples in space. They are proof that even the emptiest parts of the cosmos are alive with motion, energy, and beauty. They remind us of our place in the universe, inside a fragile, magnetic bubble, protected by a small bow shock, surrounded by a galaxy filled with countless other arcs and waves, all part of the great cosmic story. Please like, comment, share, and subscribe to the channel.